Hello everyone, welcome back to 3 Deviations. So in today's video of single variable calculus, we are going to be covering some distance optimization. So this is fairly similar to coordinate optimization, but this is kind of a real life application. So say you're maybe driving your car on a highway versus on a surface road from one place to another, and you want to see which road you should take. So that's quicker based on what speed and the distance that you'd be traveling on each of the roads. It's something similar to that, where you have variable speeds that you could be going at that could affect your estimated time of arrival. So as always, just refresh on differentiation if you haven't already, or if you don't know what it is, please go watch Unit 2. So let's get started and do some distance optimization here. So the problem today is that a boat is launched from a point A into a 3-kilometer wide river. So point B is going to be 8 kilometers downstream from the opposite bank. And then we're going to have point C on the other side of the bank. So the man rowing his boat is going to be able to row 6 kilometers per hour in the water, but then he could run 8 kilometers per hour on land. So where should he go to shore that ensures that he gets to point B in the least amount of time? Right, so I think a picture is going to be helpful. So why don't we draw the riverbank, right? So we're going to have a distance here of 3. So we have 3 kilometers there. And we're going to have point A here. Right, there's A. And then we're going to have point C here. And then point D is going to, or point B is going to be here. And then point D is going to be somewhere along this area here. And we'll call the distance between C and D, we'll call that distance x, because that's going to be variable. Then we already know that the distance here is 8. And we want to figure out where we should put point D so that we can go as quick as possible. And in this problem, we should probably be assuming that the flow of the river isn't really going to be important. It's probably going to be negligible compared to the speed that he can row at. So, well, what should we start off first? We should probably make our distances, right? So when I make my distances, I'm going to want dB and AD. So the distance between D and B is going to be 8 minus x. So we have 8 here, we have x here. The difference is going to be this here, right? And then if I want AD, well, I can use the Pythagorean Theorem. I'm going to have, this is going to be 3, that's going to be x, so then this distance here is going to be the square root of x plus 3, x squared plus 9, right? And that's just using the Pythagorean Theorem. All right, so now we can make our function that will tell us the total time taken, because we know that velocity is going to be distance over time. So of course we can manipulate this and solve for time. So here we are going to just be doing distance over velocity equals time. So we have the distance AD over the speed. He can do in AD is in the river, so we know he can do 6 kilometers per hour in the river. And then we have 8 minus x is this distance between D and B, and that's 8 minus x, and that's over 8, which is the speed that he can run at, which is 8 kilometers per hour. All right, so now we have a function here, t of x. So now what we need to do is minimize this function. All right, and this is some fairly easy differentiation that will lead us to an answer for the derivative. And that will give us dt by dx is equal to x upon 6 times the square root of x squared plus 9 minus 1/8. All right, so now we need to solve for 0 here. And to solve for 0, we just need to do some algebra. And when we solve for that algebra, that is going to give us an answer of x equals 9 over rad 7. So we have successfully done the hard part. We've used the calculus, we've set up the problem. Now we just need to make sure that that's our actual minimum value. And to do that, we just need to evaluate at the endpoints. We need to evaluate for the case where x is equal to 0 and then x is equal to 8, because that wasn't accounted for yet. If you remember, we still need to make sure that our endpoints aren't the minimum values. And if we do that, that will just corroborate our minimum that we have at 9 over rad 7, because t of 0 is going to be 1.5, t of 9 over rad 7 is going to be 1.33, which is less than both t of 0 and t of 8, which is 1.42. That means that our distance in the problem is going to be that x should be 3.4 kilometers downstream, and that's an approximation, of course, because we do not have algebraic numbers here that we should just put into these decimals. That will be easier to approximate. So here we have 3.4 kilometers as our final answer. All right, well, thank you for watching this problem for optimization. In the next video, we are going to be talking about one more optimization problem, and then we are going to be moving on to Newton's method, which is the last main topic in differential calculus. We'll see you guys next time. Thanks for watching.